All right, Chapter 1, Section 4 in college algebra, we're going to talk about complex numbers. We are halfway through Chapter 1 as we talk about this section. I like this one. I like this one because we're working with imaginary stuff. It's the imaginary unit I, which is defined as equaling the square root of -1. So we're going to use the lowercase letter I to represent the square root of -1 because there isn't really a square root of -1. And the other half of the definition that a lot of students overlook is that I squared therefore equals -1. It can be proven that I squared equals +1. So it needs to be a stated part of the definition that I squared equals -1. Another thing that we're going to be seeing as part of this section is complex numbers. And standard form for a complex number is a plus bi, where a and b are real numbers and I is the imaginary number or imaginary unit, square root of -1. And so here are some examples of complex numbers. -4 plus 6i is a pretty traditional looking complex number. In the next example, 2i is really a purely imaginary number. It can be still represented though using standard form a plus bi. Your a value just so happens to be a 0. And the third example is the number 3, which can be, again, represented using standard form for a complex number. Your a value is the 3, but your b value is a 0, leaving you with a purely real number. So again, the first example is a complex number, the second example is a purely imaginary number, and the third example is a purely real number, which means that the first example has real and imaginary as part of the same number. That sounds complex. A complex number is simplified if it is expressed in that standard form a plus bi. We can say that two complex numbers are equal to each other if the real components, the a and the c values, are equal to each other, and the imaginary components, the b and the d, are equal to each other. We can perform operations on complex numbers. We can be adding and subtracting them together, and you do what you would actually end up doing if you didn't know anything about complex numbers, is you would do some distribution and combine like terms. So let's do that. In this example, we're being asked to subtract, and I'll show my work. So we need to do some distributing here. We could also think of this as 3 complex numbers. I wasn't going to do it that way, but let's do it that way. Let's think of this as 7 plus 0i, and then we're subtracting a -9 plus 2i, and we're subtracting a -17 minus I. I think I'm going to kick myself for doing it this way, but let's try it anyway. Hopefully that's not the right answer because it's in my way. What is 7 minus -9? That's like 7 plus 9, which is 16. And then we have another double subtraction down here, so that's going to work like additions. We've got 16 plus 17, which makes 33. Let's look at the imaginary components. We've got 0 i's, or 0i, minus positive 2i. 0 minus 2 makes -2. Minus -i. That's like plus I. So now we've got -2i plus I makes -1i. A was not the right answer. C, however, is the right answer. 33 minus I. So that's one way to solve this problem. The other way would be a technique that's probably more instinctual for you, which would be to distribute this minus sign and distribute this minus sign and then combine like terms. So that would be 7 plus 9 minus 2i. Can I fake that in there? Not so much. Minus 2i plus 17 plus I. And if you combine like terms, there's the 7 plus the 9 plus the 17, which gives you the 33. And here is the negative 2i plus I, which gives you negative I. So we get the same answer. So two different techniques for solving the same problem. That was subtraction. You can imagine addition wouldn't be very different from what we just did there. Here we've got multiplication, so let's find the product of these two complex numbers and then write the answer in standard form. This shouldn't be too difficult. This looks like stuff I've done before. I bet you we're going to FOIL. And you're right, we are going to FOIL. 8 times negative 3 makes negative 24. 8 times positive 9 is positive 72i, because it was positive 9i. Negative 4i times negative 3, the double negative makes a positive 4, and 3 makes it 12, and don't forget that multiple of I. And then the L in the foiling process says negative 4 times positive 9 makes negative 36, and I see a lot of students forget this. Please don't be one of them. This is a negative 4i times a 9i, and if it said 4x times 9x, wouldn't you multiply the x's together and get x squared? Well, you have to do that here with the i's. This does turn out to be negative 36 or minus 36i squared. We could put an equal sign over here to the left. Now the next step is pretty intuitive. We're going to combine like terms here. Normally I don't do my notation like this. We've got plus 84i. And then we have minus 36, and don't forget that I squared is equal to negative 1. So this really says minus 36 times negative 1, which is going to turn it into, and this is where if you had a highlighter, you could highlight the I squared and the negative 1 so that when you're going through your notes, it catches your I and reminds you to make that conversion. So we've got negative 24 plus 84i plus 36 now. Negative 24 plus 36, switch it. Do it as 36 minus 24. That makes it a pretty obvious 12. I'm writing the 12 first. That's the real term or the real component. I'm writing the 84i second. That's my imaginary term. And I have written my final answer in standard form for a complex number, a plus bi. So this is pretty straightforward foiling and combining of like terms. Just be mindful of this one additional maneuver where the I squared has to be converted into a negative 1 and then dealt with. And this problem even told us, as a reminder, to write our final answer in standard form. So you do need to know what standard form is. Complex conjugates and division. For every complex number, a plus bi, it has a complex conjugate, a minus bi. The only sign that changes is the one in the middle, from a plus to a minus or vice versa. The interesting thing about, complex conjugates is that when you multiply them together, when you FOIL them, if these two complex numbers had been complex conjugates, and here's the f and the O and the I and the L, if these had been complex conjugates, the O and the I terms would have been opposite one another and they would have canceled out entirely, and you wouldn't have any imaginary term left at all. Hi. Do you want to participate? Do you have something to say? She's staring me down. Come here. Come say hi. And then I'll put you back down. We have 3 cats. This is another one of them. This is Luna. Say hi, Luna. Say, put me down, Luna. Okay. So let's see how that plays out when we actually work with complex conjugates. Here it is very generic. We're seeing that these complex conjugates, the positive one is first, the negative one is second, foiling has been completed, combining like terms has been completed, and you just have these real numbers being squared and added together. And if you switch the order and put the one with the minus sign first, doesn't matter. Foil, combine like terms, no imaginary term. So we just had a bunch of conversation right now about foiling, which is multiplication. Doesn't it make sense that the very next question says divide? You'll see that it does make sense. We're going to divide, but we want to express our final answer in standard form. The very first thing that we're going to do in this division problem is multiply. I love it. I'm going to take the negative 6i over 3 plus 2i, and I'm going to multiply it by a fraction. The value of this fraction, here it is equal to 1. Multiplication by 1 doesn't change the value of the given expression, but it's going to change what it looks like. Anything divided by itself is equal to 1, so the top and the bottom of this fraction are going to be identical to one another. What are they going to be? It's going to be the complex conjugate of the other denominator, the original denominator. So here it is, complex conjugate. You could highlight this or maybe come in real lightly with a pencil or something, and will that work? So there it is, equals 1. We're using multiplication by 1. Good. And now we have to actually do the multiplication. Sorry to be the bearer of bad news. So in order to make the most sense out of that, maybe we should write this one more time. Let's write it as one big fraction. Let's write this as negative 6i times the quantity 3 minus 2i, all divided by, and then we'll put these complex conjugates in parentheses. We can put an equal sign to the left of that because those two expressions are equivalent to one another. And then let's multiply. In the numerator, we're going to distribute. In the denominator, we're going to FOIL. In the numerator, I've got, let's put this division line here, negative 18i plus 12i squared. I'm going to go ahead and leave it as 12i squared for the moment. In the denominator, let's FOIL. We've got 9 minus 6i plus 6i minus 4i squared. You can see it already in the denominator. The O and the I terms are going to cancel each other out. we could have used this shortcut that we see right at the top of the screen, knowing that the product of the conjugates is going to eliminate the O and the I terms. All we had to do was square the A and the B. That's the 3 and the 2, right? And there they are, 3 squared, 2 squared, add them together. In fact, we know that they're going to be positive. Something squared is going to be positive, B squared is going to be positive, A squared is positive, adding them together no matter what. So that's a nice shortcut if you start to recognize that pattern and think to use it. Otherwise, just FOIL it out carefully. You'll still get the same correct answers. Okay, let's just start cleaning this up. If you want to put in your little note over here that this is equal to -1, you could. So that allows us to write our numerator as, see what you think of this, -12 minus 18i. Right, because what's positive 12 times -1? -12. And here's the -18i. And since they're connected by addition, or really subtraction, once that becomes a -12, you can take the order of those two things and swap them around because they're maintaining their signs. Okay, it's still a -12 and it's still a -18i. In the denominator, the -6i and +6i are going to cancel each other out. If you want to put a line through them, you can. If you want to take my recommendation and circle them to indicate that they're going to be canceling each other out, or do it really lightly so that it's still legible later when you're reviewing these notes, that's my recommendation. And let's write this as 9 plus 4. And if you want to use your other writing utensil and come in here and put a note that this really says -4 times -1, which is what turns it into a +4, so that we can add it to the 9. Frame it up however you want so that it'll make sense to you not just now, but also later when you're reviewing your notes. All right, we're almost there. -12 minus 18i, all divided by 13. Is there anything else that we can do? Can I combine more like terms? Can I square another I, etc., etc.? Doesn't look like it. Is this in standard form for a complex number? The answer is no. How do I take this and, the numerator is a complex number, but it's being divided by that 13 down there. So what's the final maneuver? It's this. We're going to distribute the division. That is in standard form for a complex number. What's my A value? It's -12 over 13. What's my B value? -18 over 13. This I'm going to put a box around as a final answer. Every once in a while you'll see an author present this in a slightly different way. And they'll put the I up in the numerator. I don't like that. It doesn't look enough like standard form. It doesn't look enough like A minus BI to me. I want this B and this I to be separate values connected by multiplication. That's not what's happening here. It's equivalent to the way that I like it written. Okay, it's equivalent to writing it that way, but the way that I did it makes that B value very distinct. And I like that. Plus, I think it makes more sense to your eye and therefore to your mind, and is hopefully helpful to you. Okay, so that is division by a complex number, which ironically starts off immediately using multiplication, and interestingly, multiplication by the number 1. What else do we have? This is it. This is the last problem in the section. Principal square root of a negative number. Okay, the square root of -b is equal to I times the square root of b. Why would that be, if you'll pardon the pun? the square root of negative b is also equal to the square root of negative 1 times b, which is equal to the square root of negative 1 times the square root of b, which is equal to I times the square root of b. That's how that really plays out. That's how it really factors out. And this that's really a property of the square root function that says that we can do this. We can take it and kind of break it up into these two components. So nice reminder for you that that is a feature of square rooting, and that's the real story behind where that I times the square root of b came from. Okay, let's take this last expression and clean it up. Since we're working with an expression, we can't do to one side what we do to the other because there are no sides, but we can use our tricks like adding 0 or multiplying or dividing by 1. Let's see, how should we do this first? How about, well, we were just talking about sort of modifying the thing that looks like this. So why don't we go in and kind of tear that apart? Equals negative 12 plus, I'm going to take the I out of there, and now I've got the square root of, now let's do it in more steps than that. Let's write it as the square root of, I'm going to do it the way that I want to do it. I'm going to write this as 4 times 7 times negative 1, all over 32. And of course, I'll tell you why it is that I chose to do it that way. I factored the 28 into these three separate factors, the 4, the 7, and the negative 1, and I chose those very specifically. I didn't use 2 and 14. Yes, 2 times 14 equals 28, but it's not helpful at all. It's helpful here because I can actually take the square root of 4. If that said the square root of 2, I'd have to leave it there. And if this said the square root of 14, I'd have to leave it there. Well, I have to leave the square root of 7 there anyway. But at least the 4, I can square root and turn it into a 2. And this square root of negative 1 down here, that's obviously going to turn into an I. So let's see where this goes. Negative 12 plus 2 times the square root of 7 times I, and make sure that that I is outside the square root symbol, all over 32. Sometimes you're going to see the I wedged in there between the 2 and the square root of 7. I don't like it. I don't like it, and I don't like it, and I don't like it. Let's distribute our division. We could even put a little dist over here. Cats are so strange. Love them, beautiful. They keep themselves very clean, but they're weird. If the I had been wedged in between the 2 and the square root of 7, there's no way I could have written that second term like that. You know that I like to have the I off on its own so that the b value is there to the left of the I, in this case 2 root 7 over 32, which we're going to simplify, but I don't know, I wouldn't get in the habit of putting the I in between those values like that. If you want to put a little note here that says simplify, or maybe you want to write simplify both or something like that, 12 and 32 are both divisible by 4. 4 is 8, 16, 32. It's good times. Good times. I was just listening to a podcast about this guy's a neurologist anyway, and it's that idea of that reward system in order to keep churning through material that's like this, right? Information that doesn't really blow your hair back, that you don't get super excited about, but you need to keep pressing on through this algebra class, for example. And you can't just feed yourself these fake rewards, whether it's chocolates or I don't know, buying yourself a new set of earrings every time you get a better than an 80% on a homework assignment or something like that. Whether you're doing the purchasing or it's a friend or a parent or somebody. But realizing that you did indeed get one more problem correct, realizing that even though it's imperceptibly small progress, that when you get a correct answer, you are indeed getting closer to that point where you're going to do well on that exam, which gets you even closer to getting the grade in that class, which gets you even closer to never taking another algebra class ever again, maybe, which is your ultimate goal, right? For a lot of people. So keep celebrating the small wins. Keep patting yourself on the back and applauding yourself for making it through one more lecture video, one more homework assignment, and successfully prepping for one more test. And try to keep those positive vibes up and those neurochemicals, as this guy was talking about, because those are the things that really help to push us through. He was talking about Navy SEALs and how the cold water and the sleep deprivation and yet they still keep pushing forward. And it's not the physical strength or the food that they ate 36 hours ago that's keeping them moving. It's that positive mindset. So keep at it. I'll keep knocking out videos and doing my best to explain these topics to you, and I will see you again in 1.5. Thanks.